that gives us the power of doing this. You may have heard sometimes people say things like, if you're proving something by induction, it's often easier to prove a stronger theorem, precisely because your conclusion is sort of also your hypothesis, your strengthening. And the same thing is true here. If we couldn't figure out a clever way to do that, well, we could have chosen one with the sum as small as possible and something else as small and something else as small as possible. And then, oh, okay, well, when we get down to here, we can adjust that accordingly. So in bigger situations, this is kind of a, I don't know, toy example almost. But in bigger situations, if you ever have the stamina to read through some of Robertson Seymour's papers, Paul Seymour give a talk, he'll do all sorts of things. He'll choose an example where this is minimized at this, and then give a whole list of things and ramp that up into an impressive contradiction. Anyway, so I want to just kind of show you that idea there, because that's often very useful. Back to a few definitions. Bipartite. I don't think I officially used that word, but we basically did when we constructed that other graph last time. That was a bipartite graph. What does bipartite mean? It means we can take the vertices and partition them into two things. I often put x u dot y for disjoint partition. Other people like to use the square u. Probably I should use that, I don't know. My square u's look rounded though, so I go to here. This is disjoint partition. Maybe I'll switch to the better notation someday. Also written x like that. And what can we say about this? Well, if you look at the endpoints of any edge, intersect x, and you look at that intersect y, and how many of them are there, each of those equal to 1. And said in plain language, it should mean every edge has one edge, every edge has one end on the x side and one end on the y side. It goes from left to right if you want to think, or top to bottom. You don't have to draw them left to right like that. It's often convenient, but they're not necessary. And I would also put this other thing, which sort of seems to have nothing to do with it, but it looks very similar. A graph is disconnected if the vertex that can be partitioned as x, disjoint union of y, such that both endpoints are in x or both endpoints are in y. And I could have been kind of really kind of clever here. And I could have said psi of e intersect x equals 2 or 0, and psi of e intersect y equals 0 or 2. Oops, this is not moving. Or I could have been even more clever and said psi of e intersect x not equal to psi of e intersect y, and here I could have said psi of e intersect x equal psi of e intersect y. Right, if they're both equal, they have to do, I guess it's got to be 1. And if they're not equal, one's got to be 2, one's got to be 0. So, and the reason I say it, because now this looks almost identical. Oh, it's bipartite, yes. Disconnected, no. So these are like the complements or the opposites or something. Like the negative of a bipartite graph is a disconnected graph or something like that. And I mentioned how close you can massage these definitions into looking, right? All that you really need is that vertical slash there and the actual word. But that kind of cuteness doesn't really pay off because no, they're not. The complement of a bipartite graph is not necessarily disconnected or the other way around. And it's not true that every graph is bipartite or disconnected. You can have both or neither. So somehow, despite looking almost identical, these two definitions, they talk about very, very different things. Now, could it be that there are some graphs for which these kind of match nicely? Yes, and I'll let you think about that. But here's an example, bipartite graph, and